Computer, yes.
We are now.
There we go.
Okay, we are. I just. Sorry, I've just lost the screen. Okay. Go back up again.
Okay, so I wasn't serious about you starting again. That was a
No,
joke.
no, it's just there we go. So I work in the Future Launch Preparatory Program of the European Space Agency. We prepare the future elements of rockets. That's propulsion. This is what you're seeing here is an engine hot fire test. I mean, hot fire, obviously it's hot, where we what we try and do is put lots of new different technologies together in a system and then test it in a representative environment. What you can't really see in this picture is that in fact there's a vacuum chamber. So we've put our engine, which is going to work in space, we've tested it on the ground in a vacuum chamber. So we're trying to be as representative as possible. This was a really cool project because we were also really putting in new things that don't exist yet or are really kind of groundbreaking for Europe. We have electric valves. I know that sounds completely normal, but we have big pneumatic ones at the moment, Ariane 5. These are smart electric valves that can do all sorts of fancy things. We have laser ignition as well. Again, that could be easy. It's really not easy setting fire to something in a very controlled manner. And what was really good fun was also, and you all know about this, 3D printing. 3D printing is a big thing for us. And especially on propulsion components. Engines are complicated, complex structures. 3D printing can really help us simplify them, and so therefore making them cheaper and easier to make. On the example we had is on the injector head on this engine. An injector head has over 200 separate parts. Normally, here we just printed it in one part. So that's obviously a lot cheaper and easier to make. But then we have problems with the fact that we can't control it like we're used to, that we used to control 200 individual parts before assembling them. And now we have one part that's printed and we have to work out how we're going to check that it works properly before we set fire to it. I also do things at the moment on structures, upper stages, carbon fiber. All of our tanks at the moment are propellant tanks are in metal, and we're looking into carbon fiber structures as we think we can really design new upper stages and new tanks using carbon fiber and optimizing the structure. But we have to again make sure this time that it doesn't catch fire, that when I put oxygen with carbon fiber, I don't get a fire where I don't want one. Right. Now I'm going to talk about rockets. The basics of rocket science. I'm assuming you all know it already. But first point for me is, what do rockets actually do? So why do we have rockets, and what do they do, and what do they need to do? And if we work out what they need to do, then we can start working out how we're going to design a rocket. A rocket transports things, obviously. So it transports things like astronauts. So not European Space Agency rockets. Ariane 5 Vega don't transport astronauts, but they do go up with the Americans at the moment and the Russians. And you can have, you'll see a nice photo of Tim Peake, who is a UK astronaut working with the European Space Agency. They transport satellites, obviously, so around the Earth. Communication satellites, Earth observation satellites. The one you've got on the picture on the left here is in fact Aeolus, which was launched last year or 2 years ago by Vega, which is an amazing instrument. It's a laser, a space-based laser used to measure accurately wind across the world. This is a space laser for peaceful purposes, unlike other space lasers you may have heard of. Rockets also transport scientific missions beyond Earth orbit. So I've talked about astronauts in low Earth orbit. I've talked about Earth observation and Galileo, GPS positioning low Earth orbit. We also could go out into the solar system and explore all the planets and the sun in our solar system. The example is the Jupiter Icy Moons Explorer, which is currently in testing in our technical site in ESTEC in the Netherlands before launch, and Bepi Colombo, which was launched by Ariane 5 in 2018, and it's on its way to Mercury now. So next thing is, I'm telling everybody, oh, we're going into space, rockets send this stuff into space, but in fact, I mean, where is space? It's an arbitrary line called the Kármán line, which is 60 miles up, and that's, I said, it's just completely arbitrary. We say by then there is so little atmosphere, we might as well call it space. And that's the line that all these space tourism companies, they're trying to get people above that line. Once they're above that line, they can say they're an astronaut, even if they haven't ever kind of done a full orbit of the Earth. So 60 miles isn't actually that far. If you think about it, it's less the distance from London to Brighton. So that would be easy to travel, unless you're trying to take the train, of course. 60 miles, that's easy to go, but we want to go 60 miles up. Now, why is going 60 miles up difficult? Because there's gravity pulling us down. There's also, we can also talk about the atmosphere, the fact of the atmosphere is actually quite heavy, even though we don't realize it, and we have to get through miles of atmosphere. And our rocket has to be designed to reduce the friction as we go up through atmosphere and make sure there's not forces as it moves, as it turns around in the atmosphere, breaking it. But the main issue is gravity. Gravity, you can visualize it, and I'm sure you've seen things like this before. We talk about a gravity well, we talk about a kind of mat of space-time, and everything that has a mass is pulling down and making a drop in it. If we want to get out of the gravitational attraction of the Earth, is we need to get out of this well. Now, the well, the depth of the well is linked to the mass of the planet, of the body that we're talking about. So as we can see here, Earth is a lot heavier than the moon. So the well of the Earth is a lot deeper. It's a lot easier to get away from the moon than it is to get away from Earth. So when we want to get away from the gravitational attraction of the Earth, we have to get out of this well. And what do I mean? We actually have to go 240,000 miles away from the Earth. If we manage to go 240,000 miles away, then we're at the top of the well. We're outside the gravitational attraction of the Earth, and we can actually then, it's a lot easier to go where we want. So if we're going to go in and explore Jupiter or Mercury, we need to get out of the Earth's well. And then it doesn't really take a lot of impulsion, a lot of thrust to get anywhere, because then there's no gravity pulling us away and we can just go where we want. So that is a lot harder, getting to the top of the well, than going just up 60 miles. But I think you can see that I've written something called LEO, so low Earth orbit, and that's where the space station is. International Space Station, for example, is orbiting in a low Earth orbit, and that's 250 miles up. So that's definitely not outside the gravitational attraction of the Earth. So satellites, a majority of satellites are still remaining within the gravitational attraction of the Earth, is still in this well. So what are they doing? How are they staying up and not falling back down? And that's to do with their speed, in fact. If you give your payload, if a satellite has what we call orbital velocity, then it's going to stay up and not fall back down the well. So this is a velocity that the rocket needs to give its payload, its customer, its package. So once it puts it into space, this package needs to have the speed to stay in orbit. And how can I kind of present this idea? I'd normally do with this tennis balls, but I don't think this is going to work over Zoom. If you drop something, it just falls back down to Earth. That's gravity pulling it down to the center of the Earth. If you drop something, if you throw something, it falls back down, but it has horizontal velocity, and then it falls a bit further away from you. And the harder you throw, the further away your object is gonna fall. And in fact, and I hope we all agree, the Earth is a sphere. So at some point, what if I throw the ball so far that it only starts dropping as the Earth starts curving away? So this is what the sphere is now in orbit. So if we don't have enough horizontal velocity, we fall back down. But if we do have enough, and enough is 9 kilometers a second, then we can stay in orbit. If we are up in space and we're going at 9 kilometers a second, then we will fall around the Earth. So in fact, satellites are falling in permanence, but they're falling with enough speed that they never quite catch up with the Earth. And if we want to completely get out of the gravitational attraction of the Earth, get out of the well, then we need to be going at over 9 kilometers a second, so over 20,000 miles per hour. Well, over 24,000 miles per hour if we're going for escape velocity, which is getting outside of the gravitational attraction of the Earth. So if we're going to the solar system, if we're going to Jupiter, if we're going to the sun, we need to be going, the rocket needs to give its payload this much velocity in order to get out of the gravitational attraction of the Earth. So we know what the rocket needs to do now: take a payload into orbit, take an astronaut, take a satellite into orbit, go up at least 60 miles and give the satellite at least 20,000 miles per hour speed so it stays up. Next point is how will we do that? So the first of all is we choose a good launch base. So here you've got another photo of me on launch base. So you can see the Ariane 5 launch zone. As I said, we launched from French Guiana, which is in South America. It is a really good launch base for a number of reasons. First of all, it is it's not quite empty. It's a big, very sparsely populated area. And in fact, the launch base zone itself is the size of Martinique, one of France's islands in the Caribbean. We've got a lot of room to do the activities we need to do. And because our activities literally involve explosives and fire, we have buildings are very far apart, so nobody can injure anybody else. French Guiana is on the coast. And as I said, you want to launch east because of the rotation of the Earth. The rotation of the Earth, if you're launching into geostationary, geotransfer orbit, certain orbits, you want to use the rotation of the Earth. You've already got 300 meters per second of speed of the Earth already, which is 300 meters less that your rocket needs to do. So being near the equator is good, and then being able to launch over the ocean is good so that we can drop bits of the rocket on the ocean and not people's heads. As you can see that the coastline of French Guiana, in fact, it really allows us a very, very large launch window. We can launch from north down to east, and we'll still be launching over the ocean. And the last thing about French Guiana is that it's very stable, geologically stable. There are earthquakes occasionally, comes as a bit of a shock, but there are not many earthquakes, there are not many typhoons or storms like this, so it's a relatively stable environment for us to operate in. Then just for the anecdote, I'm holding up 3 fingers on the photo because the tiny rocket behind me, it's Ariane 5 that we're taking out to the launch zone for the 3rd time. We'd already taken it out twice, tried to launch it, it didn't work, took it back into the assembly building, disassembled it, reassembled it, and took it back out again. This was the 3rd time we're doing that, and we were really hoping it was going to work. And it did. 3rd time lucky, and I finally managed to get home. Next thing a rocket needs to do is get off the ground. This is obvious, I think. Your thrust needs to be bigger than your weight. So thrust, the weight being the raw mass multiplied by the Earth's gravity. So it's easy, everybody can kind of jump up, but very quickly we're pulled back down to Earth. A rocket needs to permanently have its thrust higher than its weight when it takes off, but as it goes up through its flight to make sure it's never pulled back down to Earth. To give you an idea of kind of the weight we're talking about, Ariane 5, when it lifts off, when it's fully fueled on the launch pad, it weighs 780 tons. So this is about the same mass as a Eurostar train that I used to be able to take between Paris and London. Haven't done recently. Also, to put this in comparison, so Ariane 5 is 780 tons at liftoff. James Webb will be 6 tons. So there is 774 tons of rocket just to get 6 tons into orbit. Why does it take that much? Why are we so heavy? It's not because of this equation, it's because of the physics, but this equation helps explain it. This is Tcharkovsky's rocket equation. So this was published by a Russian scientist in 1903. So the basic ideas of rocketry was already around in 1903. And it actually tells us a number of things. Delta V is the speed, the difference in speed you want to get. So I said we want to go to orbit. If we want to get up into an orbit, we need to be going from more or less 0 to up to 20,000 miles per hour. And that is dependent on this figure ISP, which is called specific impulse, which is a measure of how efficient your engines are. It's dependent on the gravitational attraction. So that number is dependent whether you're on the Earth or on the Moon or on Jupiter. That number is different depending on the size of the planet trying to get away from. And then it's very much a function of these 2 numbers, which is your initial mass and your final mass. And what is the difference between your initial mass and your final mass? Well, it's the fuel you burn up as you go up. So the more fuel we can burn, then the faster the speed we can get at the end. So we could say, well, okay, I want to go really fast, and I'm just gonna have 800 tons of fuel, and then I'll burn all that in one go, and job's done. Problem is, we go back to the thrust over weight. We don't know we're not sure how to have engines that can have enough thrust to get that weight off the ground, and we're not sure how to have structures that contain that fuel that are light enough so the overall mass of the rocket is again light enough for us to actually get off the ground. So what we can do let's just go. There are always has been a number of, there are ongoing studies about single stage to orbit rockets, and we've heard about the Skylon, the space plane, and these are ideas where we also use air breathing engines or switch between air breathing and rockets. There might be a way to do this in the future where we take some of the propellant comes from the air, so we are lighter over on the rocket. At the moment, this is the way we found it. The best way to do it is to take this equation and then just split up the rocket into bits. And each bit has a certain function. And once we've finished with it, we drop off that stage, that bit. We don't need it anymore. The empty structure goes away. And then the rest of our rocket is lighter and it's easy to get up. So what is very important about a rocket is being as light as possible. And then as soon as we don't need the mass, we'll drop it. So I try to explain that the staging principle to you with this Vega. So this is a Vega rocket. It's also launched from French Guiana. Now, in fact, I'll start from the top. Vega can launch 1.5 tons, can launch a Hippo into space, 1.5 tons of satellite. The last stage of Vega is a storable liquid stage and has 0.5 tons of fuel, so about a polar bear's worth of fuel. That is the fuel you need to kind of, once you get into orbit, to get that final positioning of the satellite. But to get the Hippo and the polar bear kind of up through the top of our atmosphere, you need 2 elephants worth of fuel, 11 tons worth of fuel. To get the 2 elephants and the polar bear and the Hippo up through a large part of the atmosphere, you need a Camarasaurus's worth of fuel, 24 tons. So Camarasaurus is then taking 2 elephants, a polar bear and a Hippo into space. And then to get all of that off the ground and to get that thrust, that energy we need for all of this to get off the ground and kind of start the first part of flight, we need 88 tons of fuel. So blue whale ton of fuel. And as soon as that 88 tons of fuel is burned up, then we drop the first stage and the rest of the rocket goes on. And that's how we found the easiest way to build a rocket. So when we have a rocket idea of what we want to do, where we have an idea of the engines we want, the final payload performance we want, then we take the orbit equation, we take the rocket equation, and we try and optimize the size of our stages based on the propellant we've got. We try and optimize the rocket 1, 2, 3 stages to try and get the best performance for the lowest cost.
Kate, can I ask a question here?
Yes, please.
There must be a point where, however much fuel you have, you just can't get enough thrust to lift it. I mean, there must be a cutoff here. You know, I would have thought if you have, I don't know, a house, whatever sort of rocket, however many tons of fuel, you know, unless you've got a bomb under it, it just isn't going to take off without disintegrating everything.
Yep, it's all a balance and a trade-off, and it's very hard to find the sweet spot between the maximum amount of fuel, the size of your structure, the power of your engine. I said also we have problems if your structure, if your rocket ends up being too long, then you end up having bending moments as it goes through the atmosphere. I don't know if you remember the Ares 1 launcher from NASA that flew once. It was a big long thing that kind of wobbled a little bit as it went up. So you've got to take, this is why system engineers are important, you've got to take all sorts of parameters into account and hope that you find a solution. And it's not easy to find one.
I mean, this is 120, oh no, it's more, it's 126 tons. I forgot the Hippo. It's 126 tons of fuel.
Yes.
And it's hard for me to conceive that any rocket is going to lift 126 tons. It obviously does, but that's an amazing amount of thrust.
This is a small rocket. I'd just like to point out.
Is it really?
Yes, Vega is a small rocket. Like I say, this is 100 and something tons at liftoff. Ariane is 780, and I Saturn 5. I can't remember, but we're talking hundreds, thousands of tons at liftoff.
Oh,
so
God.
You need an extremely powerful yet lightweight engine. So you need a rocket engine. Basically, there's no other way we can do it. There's no other engine that's going to give us the performance we need. It's not going to be a car engine, and it's not going to be a plane engine. We need something that's extremely performant, extremely efficient, extremely powerful, depending on where we use it. On the first stage, we have powerful engines. On the upper stage, we have efficient ones. We don't need thrust on the upper stage. We need performance. So what is a rocket engine and how does a rocket engine work? Again, the basic idea is really simple, actually, and then trying to find the real solution is hard. Rockets just are containers that spit out fuel, that spit out gas. And it's action reaction. When the gas goes out one end, then the container moves forward. Obviously, the more gas the heavier gas, the faster the gas can go out one end, the faster we can move forward in the end. In fact, the speed of the gas leaving our container defines the maximum speed we can reach. And that's, for example, why we use hydrogen and oxygen in Ariane 5, because that has a very efficient reaction and has extremely high exit speed when you come out of the nozzle. But also the problem with hydrogen is that it's extremely lightweight. So I've also said I want to have a maximum mass flow, but hydrogen is extremely lightweight. How do I get a huge amount of mass flow of hydrogen going through my engine? And this is when we start having things like increasing the pressure inside the tank. So you have a high pressure tank, then your gas gets thrown out quicker. But the problem with a high pressure tank is that it's thicker. You need a thick tank, and then it's heavier. So what we do for rockets, again, Ariane 5, the main stage is so light it cannot stand up by itself. It's actually hung off the side boosters. That's how thin the propellant tank is. So it's obviously not highly pressurized. What we do instead is we use turbines, turbo pumps driven by turbines that are driven themselves by the fuel, that go up to speeds of, the hydrogen turbo pump is insane. It's something like 80,000 RPM. It go around very fast and enable us to get as much propellant through the engine at any one time and get the thrust we need to take off. But we also see for Ariane 5 is we have the main engine. You see this on the next video. The main engine ignites, but the rocket doesn't go anywhere. It's when we only when we ignite the solid boosters, and solid propellant gives us, it's less efficient, but it gives us a much more thrust for the size of the engine. So a lot of solutions we have are using solid boosters just to get us off the ground. So as I just said, here we have a nice video of an Ariane 5, and this is how it gets off the ground. It's got the staging, it's got the rocket engines, it's got the launch base. And I said what you see now is the Vulcan engine ignites. We check it out. Okay, the engine seems to be working. Then they'll ignite the solid boosters, and that's only when we take off. That's the only, then from that point we have thrust above weight. You see all the birds don't approve of the launch. It gets them out of their nests. What you'll see now is, in fact, the launcher takes off vertically to get off of the launch pad, to get away from the lightning rods we have down there, and it'll start turning now in a move what we call a gravity turn. So in fact, it's very inefficient to fly straight up because gravity is pulling us straight down again. So it starts, as soon as it can, it will start turning over so that it starts flying more or less horizontally, so the effect of gravity is reduced. Right, so this is all I had to say about Ariane 5 for now, except that it's a very nice launcher, and if you ever get the chance to go and see a launch, one should do it. And I just wanted then to move on to James Webb. So James Webb is a satellite that will be launched by Ariane 5 by the end of the year, fingers crossed. I said I'm so nervous about this launch, and I have nothing to do with this launch, but this is going to be, I think, the most expensive payload Ariane 5 has ever launched. Last time I heard it was something like $9 billion or $10 billion just from the NASA budget, and there are also contributions from ESA and from the Canadian Space Agency. So just to talk about James Webb a little bit, then also I'll say, I do like a bit of astronomy. I'm not an astronomer. If you have very detailed questions about the observations, I'm probably not going to be able to help you as much as I would be able to help you on the rocket. But I'll give you some first information, and then I sent some links to Paul as well, where you can also go and have a look at the some ESA information that's available on this. So James Webb is going to be the largest, most powerful telescope launched into space. It's going to observe near infrared to mid infrared. The primary mirror is 6.5 meters in diameter. So that is twice as large as the Herschel mirror, which I saw launched in 2009. And when that was launched, it was the largest mirror for a space telescope at the time. It's coated in gold because gold reflects infrared, also looks very classy. It has a 5-layer sun shield underneath it. This is the size of a tennis court. So I don't have any kind of size comparison diagrams, but you just have to imagine that silver diamond is a tennis court. You have to imagine Andy Murray running around that. And because we're looking in infrared, the telescope has to be cold. So the telescope is operational at minus 233 Celsius, where absolute zero is minus 273.15. And in fact, there's an instrument, the MIRI one, that looks in the mid-infrared that has to be even colder. I really like this diagram. It kind of shows the complementarity between Hubble, Webb, and Herschel. So everybody knows Hubble, it's been launched, it's been operational since 1990. It's been able to be operational so long, fingers crossed for the current problem, because it's been in low Earth orbit. I think it's been serviced 5-6 times by the space shuttle. And it's in low Earth orbit because it's looking into the visible spectrum. And I'll discuss a little bit the orbit that Webb and Herschel both used, because they have to be further away from the Earth because it's a noisy infrared source. So Hubble looks into mostly through the visible spectrum. Herschel looked into the deep infrared, and Webb will kind of cover the gap between the two of them. Now, it said James Webb is a NASA program. They spent an awful lot of money on it, but since 2003, ESA has also had an official participation in Webb. ESA has contributed the NIRSPEC instrument, has contributed part of the MIRI instrument, will contribute scientific support to mission operations, and will, kind of as for free, will launch it. So NASA is not paying for the launch. They're not paying for the launch operations. That is provided by ESA. In return, scientists in ESA member states can apply for observation time on the telescope with a minimum expected time of 15% of total observation time. And I understand they had their first kind of round of applications a few months ago, which was incredibly successful, at least from the European side. They had a number of applications accepted for observing time on the satellite. I said James Webb mirrors 6.5 meters, which is amazing. The problem being that Ariane 5 fairing is 5.4 meters in diameter. So we have a slight problem of just fitting it into the launcher. So it has to be folded up, like origami style, to be able to be put into the launcher, to be in the fairing, which is the protective cover around the satellite. But there are also a number of customizations, adaptations for Ariane 5 because of this very specific satellite we're talking about. It's apparently very sensitive to pressure depressurization. So they've included additional venting ports in the fairing. Obviously, when you lift off, the fairing is at ambient ambient pressure, and as you go up, well, the air comes out of the fairing until you're into the vacuum of space. They've included additional ports to make sure that this venting is as smooth as possible, and also at the moment we separate the fairing, that there's no pressure shock for the satellite. I said earlier that as soon as we don't need anything anymore, we get rid of it. It's dead weight for us. The fairing, it's after less than 3 minutes. I think it's 3 minutes into flight, we get rid of the fairing, because already by 3 minutes we're so high up in the atmosphere, there's just not enough air around to bother the satellite. So we don't need the fairing anymore. We get rid of it. We've adapted the fairing. We've adapted the installations in French Guiana. There is extreme cleanliness requirements, so we have extra cleanliness tents during the assembly operations. And then my favorite one is this, what they call oscillating rolling maneuver. Once we have the fairing open, then James Webb is open to the elements, is open to having the sun on it. And kind of the non-technical term is actually barbecue mode. The rocket is going to rotate in a way that the James Webb is constantly cooked by the sun, and there isn't one side that heats more than the other. So Ariane 5 is going to take James Webb onto what's called a transfer orbit, Lagrange L2 transfer orbit. And James Webb then will take itself to L2 points. So what is L2? L2 is one of the Lagrange points, and these are multiple points around the Earth-Sun gravitational system, where the gravitational attraction of the Earth and the Sun is kind of cancelled out by the orbital forces. So these are stable. Again, it's not a point in space, there's not a flag there. These are stable regions of space where if you put a satellite there, then you need less effort. You don't need much effort to keep in the same place. You're not being pulled right or left or by anything. You're just, every force is aligned to keep you in that place. Why is L2 interesting? L2 is one of these points, and it is kind of behind the Earth from the sun. So it's 1.5 million kilometers from the Earth. So we're away from the Earth and its noisy infrared signals, but we also have a good view. We can transmit, we can communicate with the Earth, and then we're away from the sun as well. So we have our nice sun shield in place, protecting the satellite from the sun, and then we can look into deep space, having cut off all this noise behind us. So Ariane 5 will take James Webb from 27 minutes. I think the flight is going to be about 27 minutes until there is separation. James Webb will separate from the upper stage. The upper stage itself has also had an additional battery included to make sure that it performs a kind of disengagement maneuver to make sure it gets away from the James Webb satellite correctly, and then it'll put itself in a safe graveyard orbit, as we call it. Then James Webb is up by itself, has to get itself to L2. It'll start unfolding as soon as it's separated from the rocket. One of the first things all satellites do is unfold and start working their solar panels, start getting energy to start powering up. During a launch, a satellite is very much powered down because we cannot have electromagnetic interference. So I'll start opening up, get the panels out to get some power, and then start unfolding itself. And the whole journey getting to L2 and getting self-ready will take a month to get to L2, and then 5 months of preparation before it can start routine science operations. So this is just a quick image of the process of the different maneuvers that the James Webb is going to do to unfold itself from the fairing, deployment of the solar panels and the sun shield, and then I just find it amazing. The secondary mirror is going to have to kind of pop out at some point to be just in front of the primary mirror. And all of this is this has to be, and we're not talking about millimeter precision, this is sub-millimeter precision. These things have to go exactly back into the position where they were supposed to be. And this is why James Webb has taken a lot of time and a lot of money, because it's not easy to do these things. Some of these instruments that I'm going to talk about later were not possible 10 years ago. And also, once you're building something so expensive, you have to make sure it works. That has gone under extensive testing in the US to make sure that everything will behave as it should do once it's in space, because once again, we can't go and service it like we would do. We used to be able to do for Hubble. So what is Webb actually going to do? What is the kind of astronomy we're talking about here? It's going to look back. Now, look back is, as I think you're fully aware, when you look at light from the stars, it's coming from years ago. The closest star is 4 light years away. So when we look at the light from that, it's from 4 years ago. So the further away a star is, the older the light from that star is, the older that star is for us. James Webb will be able to look back over 13.5 billion years. So that is, again, everything is relative. That is to stars and galaxies that are less than 300 million years old, which is, tiny, tiny in astronomical terms, in astronomy terms. So it's really going to look at proto-galaxies, the first stars, and the first black holes. You see black hole growth, and we really think that black holes impact, because of their gravitational influence, impact the evolution of the universe. I will also try and look into the potential impact in dark matter, see if we can get any more answers about what dark matter may be and where it is. It'll be able to look into the life cycle of stars from their birth and from their death. Infrared is useful for this because infrared can see through the dust clouds and gas clouds that are around the protostars. In visible light, everything gets scattered by the gas and the dust. Infrared doesn't get scattered in the same way, so we can actually see through these clouds into the kind of really what's going on in the heart of these protostars. And that's also the same for stars and also gas giants and planets. Everything that's kind of coming together, agglomerating, we'll be able to see this process. And it will be able to look on exoplanets. And this is really interesting because this is something I've really seen a big difference. I did a physics degree starting in year 2000. And when I did my physics degree, I remember talking about there were something like 10 exoplanets that have been discovered. And they were all, super ginormous gas giants. Now there are thousands and thousands of exoplanets that are officially discovered with all different, not shapes, but all different sizes. James Webb will be able to study the atmosphere of these exoplanets during their transit in front of their stars when the light dips and be able to do spectroscopy on the atmosphere. So be able to work out what elements are in the atmosphere of all these different exoplanets. How is it going to do this? There are 4 instruments on James Webb. There's the NIRSpec, which has been provided by ESA. It will do a spectroscopic survey of stars. So again, doing the spectroscopy mapping, separating the light into all the different spectra and trying to work out the elements that are in there. This is, all these instruments are so complex. I don't understand all the details, but I worked out it has lots of kind of little boxes. It will be able to map 200 objects simultaneously, and it will do a spectrographic analysis of 200 different objects by splitting up the light. From every pixel will be analyzed spectrographically. There's the MIRI, so that this is looking into the mid-infrared, where the optical system has been provided by ESA. Because this is looking into mid-infrared and this is looking at very cold objects in the universe, it itself needs to be very cold. This is why it's down at minus 266 Celsius. MIDI can also do coronagraphy, so blocking out the light of the star to be able to see around it, and spectroscopy as well. We have the NIRCam provided by NASA, which will be able to can do simultaneous imaging in 2 different infrared ranges, so get 2 kind of pictures of the same element, and be able to look kind of the deepest images of near infrared ever obtained. And this is what I like both for NIRCam and for NIRISS, is that these are very, very precise scientific instruments, but they're also used for this kind of station keeping for the operation of the satellite itself. Because some satellite has to be very precise about, the telescope has to be very precise about its pointing, and it has to be extremely stable. Infrared imaging, we are talking about days or even weeks of pointing in the same direction. So both a NIRCam and NIRISS will be used to help maintain James Webb in a very stable position to be able to perform the observations. And then NIRISS is provided by the Canadian Space Agency, and this is the one doing the exoplanet characterization, really doing the spectrographic analysis of the molecules in the exoplanet atmospheres. Just a small image about the spectroscopy that it's doing. Like I say, I think you're aware of this, but you get the light from the different stars from the atmospheres, and it's split up into multiple different spectra. And then we look into these lines, these absorption lines, that we know that each element has a very specific absorption criteria. It's a fingerprint, and we can look into the spectrum and see if we can see these lines. And then we can say, well, then that these elements were present in the light from that we're seeing. These elements are present in the element that this light went through, so the atmosphere that the light went through to get to us. And also with these spectra, we can actually start telling things like the temperature and the density and the motion of the object based on the spectra and their position in the electromagnetic spectrum. Why specifically is James Webb looking in the infrared? So I've already mentioned the fact that infrared can look through gas and dust, so we can look into the cores of protostars and protogalaxies. But also, I think you're aware of the Doppler effect, or so it's redshift, which is like the Doppler effect is that when an ambulance comes towards you, the sound is squashed, and as it's moving away from you, it gets stretched out. And this has happened to the light in the galaxy. As the galaxy is expanding, light, when it's emitted and as it travels across the galaxy, gets stretched out, and its wavelength gets increased and its frequency goes down. So these objects that are interesting, the objects that are really from the beginning of the universe, the first light, was actually now in the infrared spectrum. So that's why we want to look there, to be able to see the first objects in the galaxy. That's what I wanted to say. So here's some reference and sources. I've said I sent links to Paul for some of the things you can click on and look at ESA available information. And you can also just in general look at the website. I said I work for ESA STS, which is space transportation. And there's also ESA Web. If you're on Twitter, you can follow them. Their journey this year. The launch is due by the end of this year, I think not before November. Like I say, I'm really looking forward to it and slightly stressed because it has to work perfectly.
Fantastic, Kate. Fantastic talk.
Thank you.
I especially like the bit that I missed at the beginning because I wasn't recording, with you in French Guiana and the Ariane rocket and so on and so forth. But hey, we have to live with these things. Has anyone got any questions?
I've got it. It's Steve here. Just one question. Can you hear me, Kate?
Yes.
Oh, wonderful. You were saying about the payload. Sorry, the fairing for the rocket. It looked as though the payload looks to be the same diameter as the rest of the rocket. Could the payload not been increased to look like some of the other rockets that take off now, so that you wouldn't have actually had to unfold the Webb telescope? Was the reason for that? Was it drag or something like that would have been a problem?
So I don't think there's a rocket today that would fit James Webb without it being folded. slightly. And Ariane 5 is one of the largest rockets, so I'm not exactly sure of the diameter of some of the for the Atlas 4 in the US, but it's one of the largest rockets available at 5.4 meters. There are some rockets, like you said, Soyuz has a kind of boat tail where the fairing is slightly bigger than the rest of the rocket, but that's still smaller than Ariane 5. So Ariane 5 design is just kind of straight down, and it's the biggest we've got for now. And as I said, it was part of the kind of ESA contribution was offering the launch. So Ariane 5 has the payload performance, has the power to get it into orbit, but has this limited size. But I don't think you would get something, you can find anything much bigger on the market today anyway.
And I have one more question, which is for the Webb itself. You might be able to answer it. Is there a facility on board to be able to refill with coolant?
No.
Just in case in the future somebody was able to get there. It's not a filler or a nozzle or fuel cap or something.
No. So I mean, that's a really good point. Like Herschel, as I said, Herschel looked into the far infrared, and Herschel was cooled by helium because Herschel had to be, super mega cold. That's the official term, and that was limited. Its lifetime was limited by amount of helium, so it still had propellant to do station keeping, the operations, the machine, its instruments were still operating, but it ran out of helium, and that is the limiting factor. There's a limiting factor for Herschel, and I think it will be the limiting factor. Well, it's not been cooled by helium as far as I'm aware, but we can't go and service it. It's 1.5 million kilometers away. It's not going to happen in the next 50, 100 years. We're going to be able to go and service it. So it's really all by itself, and that's why it really has to work kind of perfectly first time. We can't have the optical problems of Hubble. We can't have that.
No. Hence the time it's taken.
The time and the budget. I mean, if it's worth doing, it's worth doing right. So they've decided to go for it, and this is also a point, like when they first had the ideas, I think late 1990s, and it's scientists are like, oh, I've got a great idea. I want to study this spectrum. And the engineers are like, we can't do that. That's not physically possible, that machine. And they've just spent the last 20 years developing the instruments that can actually do what the scientists want. This wouldn't have been possible 20 years ago. So they now are doing it, and we're really at kind of the edge of what science can do. But yeah, we can't refuel it. So we're going to have to get it right, and we have to make sure it works first time.
Thank you very much.
No problem.
I've got a question about
Nick,
the.
go on, you go ahead.
Hi, I've got a question about the Ariane rocket launch. I think it's in the blast pit. There was some horizontal jets of flame arriving into the blast pit.
Yeah. Is
that to reduce or to ignite something, or is that to burn off gases, or what's all that? What's happening there?
It's, I think what you may have seen is water, which is
water. Okay.
Dampening. So a large part of what it's doing is dampening the vibration energy. So effectively, launch is actually, especially takeoff, is one of the hardest things for the rocket and for the satellite. There's a lot of vibration going on because of all this energy we've let off. So there are flame pits underneath the main engine, and also underneath the boosters. There are flame pits that direct the flames and the exhaust away as kind of far as possible away from the launcher to get that energy away. And then as soon as we have ignition, we also have these dampening by water that comes on and kind of covers the noise below and protects the rest of the rocket from it, because it can't get through the water. And at the same time, that's cooling the launch table that is getting a lot of energy being put on it by the rocket engines. So it has a double effect of dampening the vibrations and cooling the launch table.
Okay. Oh, that's interesting. Thank you. I didn't know that. And then I had a second question, which was, I haven't worked it out, but L2 is how far away in light seconds, so what's the communication between us in
can my phone do that? 1.5 million.
I haven't worked it out. Probably
a million kilometers. Yeah, I can't do that. So 1.5 million times 1,000 divided by, is it? I used to know this by heart. 3.18 times 10 to the 6 meters per second.
About 3 seconds, isn't it? Or something like that.
3 seconds.
It's not. It's not too far.
It's 5 seconds, isn't it?
5 seconds, whatever.
It's not. It's pretty near then. Okay.
It's pretty near. It's not. I said that L2 is good for us. It's far enough away to reduce the noise coming from the Earth, but it's still close enough that we have not instantaneous, but we have a very close contact with it. It's not, we don't have to wait 40 minutes. Oh, there's a problem. So it's still, I mean, obviously James Webb is autonomous, but there will be a lot of contact, a lot of control from the ground to plan the science operations and the kind of what we call station keeping and mission keeping, just keeping the thing ticking over properly.
Okay. Thanks very much. Thank you.
Sorry, Paul, did you want to talk?
Yeah, just funnily enough, this isn't actually a question for Kay. It is an answer to a question that was presented by you, Steve. The Saturn V at launch, fully laden, goes at 2,950 metric tons.
How many?
2,950 metric tons.
3,000 metric tons.
3,000 metric tons, yeah.
My God.
2,950.
I mean, okay, let's put it the other way around. If you are that engine at the bottom that you showed us the picture of, that rather elegantly silvered engine, you've got 3,000 tons sitting in your head.
Yes, that's why Saturn V used multiple engines at the bottom. I can't remember. And that is, I mean, that's
Kate. This is science fiction. This is extraordinary, really. I've never seen the numbers before, really.
But this is also why I'm a rocket scientist, and this is why, in my very personal opinion, as a propulsion engineer, rocket engines are the most interesting thing on a launcher. It's, I'm not interested in car engines or plane engines at all. It's rocket engines because they are just absolutely amazing, and it is almost science fiction what they can actually do. As I said, the turbo pump of the hydrogen on Ariane 5 is 90,000, over 100,000 RPM. So there is no room for problem there. If you have a problem on that, then the whole thing explodes. And the turbo pump is at 20 Kelvin, and the engine, which is 20 centimeters away, is at 2,000 Kelvin. So just the thermal constraints and the material constraints are just incredible. It's incredible we actually get it to work.
Why do Elon Musk's keep popping?
Why do they keep exploding?
Why do his rockets keep popping when they take off in a way that, you know, we're hoping that Ariane won't?
He's experimenting, exactly. And as you know, as a rocket scientist, I would love to be able to do that to a certain extent, is to be able to see, because we have all sorts of analysis and we do predictions. And when I showed you the hot fire test before, we'd done all sorts of predictions to make sure we knew what was going to happen, more or less, but it was a new technology, so we're never quite sure. So we always kind of take it carefully. And Elon Musk is his self-funding. He can, to a certain extent, take the risk, just give it a go and see if it works, and then learn. And you really do learn by failures. And unfortunately, on a launch campaign, when you make a mistake, you really learn very quickly not to make that same mistake again.
Yes.
Elon Musk's ethos is what
fail quickly, I think.
Learn, fly, crash, learn, fly.
Yeah. He can do that as a European Space Agency. That is taxpayers' money, and I don't have the same freedom to burn it as freely.
Right. What is the insurance premium on this?
Oh, that's a really interesting question. Insurance premiums used to be an issue on for launches, because in fact there was a limited amount of insurance premium available in the world for satellite launches, because it can cost a lot of money, and when they do go wrong, they have to pay out a lot of money. And we had people from like Lloyd's of London coming to visit French Guiana to be able to better estimate the costs. And it also can feed into, and this is something where Ariane 5 used to have an advantage against Falcon, is that our insurance costs were lower because the rocket was much more reliable. So even if the rocket was slightly more expensive, overall the cost of launch was cheaper for the clients because they were paying less insurance compared to the Falcon 9 rocket, for example.
You put so much money into this. I can't imagine it's not insured. You'd have to insure it because it's just, you know, if it goes wrong, you've got nothing.
So generally, institutional, like ESA science missions, are not insured because it's taxpayers' money anyway. So it's considered almost a gamble. So it either works or it doesn't, but we don't pay insurance on institutional missions. Communication satellites, they do have insurance because they have a business to run.
So is the James Webb insured or not insured?
There's nobody that's going to insure James Webb. Nobody.
Wow. Do you know what? That is so scary a thought. I don't even like to consider that.
No.
The numbers are so vast that I can't even comprehend not having an insurance policy.
The stock markets have gone up so much in recent years. They might not have been able to insure it 10 years ago, but certainly. I mean, how long has this project been going for now?
Since end of 1990s or something, the first
Okay,
idea.
so they might have thought they couldn't insure it in the 1990s.
Yeah.
Today, they certainly can. I mean, the insurance market's got to look how much any of these billionaires has got. Any of them could insure this.
I said I don't know. For European science missions, we're not insured, but for James Webb, I wouldn't be able to say exactly. It's a NASA mission, so.
Wow.
Go
Right.
forward. Go-
Sorry, Edwin, please. Yes.
Actually, it's a family connection I'm inquiring about. I have any family connection with Professor Mike Underhill?
No, but I think I've
Sorry.
met him.
Pardon?
Mike Underhill. Does he work in something to do with kind of environment and
Yeah.
and
Yes, he's
space?
University.
Very strange. I mean, we have a very unusual surname, but as far as I'm aware, we are not related. None of my family works in space or aerospace at all.
Okay. Okay. Thank you.
Great. If there are no more questions, I'm going to say, Paul, have you got your hand up?
Yeah, I've got one more question. If you can hear me, because I've got a stable it says I've got an unstable internet connection. Right, okay. Going forward, Kate, how are things looking with reusable rockets with the European Space Agency?
Yeah, good question. Yes, we are looking into it. So as it's obviously, it's like many things, it's complicated. Let me just stop that.